Okay, so this is basically the final part of our fMRI. I mean, we were trying to look at how functional MRI works. So, I mean, what I did is um, started from a simple magnetic resonance principle. So I described that there are two-level system and you throw photons to the two-level system and they get absorbed or not absorbed. From that, you can construct what you call a spectrum. So this part was the first part, meaning how we find a spin or how we detect whether there is a spin or not. Then we mentioned that there could be spins. Spins, usually the spins we are looking at are mostly the nuclei of various atoms. In our case, we are mainly interested in hydrogen atom. So its nucleus is proton. So we are detecting proton, and proton has very distinctive, a very high frequency compared to other nucleus. So we usually detect that. Then what we described, there are two techniques. The technique one is how do we record where do we have proton. So I showed you that for that what we need is kind of gradient assisted spectroscopy. You will have to apply gradient and then record a spectrum. Then change the direction of the gradient, you record another spectrum. So if you keep doing that, then the spectra recorded for various orientations of the gradient, that will actually give you uh, some idea about where your signals are coming from. Okay. Of course, I mean, we showed for a very small test sample, but even that is good enough to understand what's going on. And the second method was the spin echo technique. We mentioned that using spin echo, we can kind of find out what is the relaxation time T2 of the sample. So these are the things what we know so far. And today in the last class, we would like to combine the two and find out how does it help in doing the functional MRI. So, I mean, there is something called MRI. I mean, apart from functional MRI. So, what is MRI? I mean, this magnetic resonance imaging is nothing but, in most cases, what we described earlier, that finding out where we have spins, where do we have hydrogen. So, essentially, when I was describing that, suppose you have some pockets of water, some pockets of water, and you are trying to find out where these pockets are. So you record a spectrum and you find some 2:1 intensity, and here too uh, 2:1 intensity, and then you also record along this direction and you find 1:1:1 intensity, and then from these information you can actually reconstruct and find out the images. What I mean to say, suppose you had no clue about what is there and you are only given the spectrum. The top spectrum has 2:1 intensity, the second one on the right has 2:1, and the third one also has 1:1:1. So what you do is you create a grid. You draw these lines perpendicular to the baseline, perpendicular to the baseline, and from there you try to look at the intersection. And these intersections, you must have intersections coming from all, coming from all. So I mean, sorry, I should not make the joint. I mean, you yeah. Now you have how many intersections here? One, two, three, four. You have four intersections, and you have to do some calculation to find out where you have which intersections are important. So, for example, this two means the two intersections are counted. Each one gives you signal. So one, two, both giving you something. So this is a possibility. In the second case, you have one here. So both the intersections, they don't have a spin, only one of them. Okay. And then these two must have something, but this along this line, it tells you either this one or this one. One of the interaction has some spins. And then if you calculate the diagonally, then sorry, this should be 2. It's passing through 2. So if you calculate, then you will have, if all four intersections are present, then you will have 1, 2, 1. If this one is not there, I mean, what we originally thought, my apologies, there should not be anything here. If there is nothing, then you don't draw anything. So you see, I mean, the line passing through this particular intersection is 3. Here too it is 3. Here too it is 3. But here only 2. So in such cases, you can easily rule out one point. What I mean to say, from all the spectrum given to you, you draw the lines, and the points where the intersections through which lines from each spectrum, I mean, at least you have one line from one spectrum passing through the target intersection, there you have something. Because if you have a pocket of water or some solution where hydrogens are present, that will definitely give you a spectrum. So if a particular line is missing, meaning this intersection, for example, it has only 2 lines, then there cannot be anything there. It's empty. So to identify n number of points, typically you need n spectrum, almost always. In this case, I mean, it's just 3, but in reality, it could be more complex structure. So this was discussed earlier. So basically, after we got the pockets, if I draw it, it will look like just this. It looks simple. It's far from the actual brain images. But then in the case of actual brain, I mean, like, let us suppose it looks like this, a very bad drawing, but it will do. You can divide it into tiny region. You can have a grid. And then each part of the grid, you can focus and check whether you're supposed to get any signal. It could be part of the skull, or it could be something which does not have much proton concentration, in which case you don't get a signal. So there would be some dark region, there would be some white region. Okay. Assuming that your proton density is more or less constant, if you can find proton, I mean, you find proton or not find proton, that will give you the eventually an image like this, what I drawn initially. So each grid point plays the role of one small pocket. Now, how many images do you need to get a spectrum like this? Actually, you need many. You need many spectrum. So it could be as large as like hundreds to thousands, depending on how good your resolution is. I mean, what kind of resolution you need. If you need very high resolution, then your number of projection will have to be very high. Fortunately, I mean, does that mean that it will also take time? Yes. In all spectroscopy, if you need more information, you usually have to spend more time. So in this case also, if you need many projection, here we did with 3, but suppose you need a couple of hundreds, and every time you change the orientation and record the spectrum, that will be a very lengthy affair. Okay. So I mean, but that is what we do. I mean, this functional MRI, that's how it works. But people found out much later that this projection reconstruction is not the only way. There are much more efficient method of recording the images. It's technically quite detailed. I think a full course can be taken on a functional MRI, I mean not MRI, how images are recorded. So I will simply leave it at that, that the projection reconstruction remains one of the earliest technique. Very early initially, that is how we used to do. And later, people found out much more robust methods. In a couple of minutes time, we can record a spectrum where you can say like multiple projections are recorded at the same time. So that is what we have figured out. I mean, that's the advancement we made. Okay. So that is MRI. MRI gives you this. And now let's move on to the functional MRI. So here we need to combine some of our known techniques like the T2 and this imaging part. Okay. So here we have a little bit of biology, which I think you know much better than I do. I mean, you are studying this neurobiology. So what I know is typically in the brain, if you have some activity going on, say for example, I'm listening to music. So in the brain, certain area might be more active than others. So this region. Usually, the brain does not store much glucose or the material that you need for burning. So typically when the region becomes active, then you have to have enhanced blood flow from the other part of the body. I mean, the heart pumps fresh oxygenated blood to that particular region of the brain. Now oxygenated blood and deoxygenated blood, they have very different, what we call T2. The transfer acceleration time is different. The main reason is, I mean, typically in a baseline state, you have a certain kind of metabolism going on. So you have some ratio of oxygenated hemoglobin and deoxygenated hemoglobin. I will just write that. Deoxyhemoglobin. So simplest spelling, instead of this AE, I'll just put E. This is what you have in the non-active areas. And in the active areas, you typically have oxyhemoglobin being brought in by the blood flow. So, I mean, what happens if oxyhemoglobin is brought in? Oxyhemoglobin is diamagnetic, and deoxyhemoglobin is paramagnetic. What's the difference between, I mean, how does it affect us, the paramagnetic or diamagnetic? Okay, it's simple. So for example, if you have a tube and we have our spins, just imagine inside, suppose we have a paramagnetic ion here. What it does is this paramagnetic ion, usually you see these are nucleus spin, and paramagnetic ion it's basically electron spin. Electron spins, they have a larger magnetic moment, so the mu of electron is much greater than the mu of nucleus. So this paramagnetic ion, it creates some magnetic field in the place of other nucleus. So that means, so these nuclei, they fill not only the magnetic field that you provided, the pulses, the magnetic field from the environment, the static magnetic field. On top of that, they also fill the magnetic field from the electron spin. So, I mean, electron spin, it's not static. It's not like it is there at one place and doing nothing. It's constantly moving, wiggling, and moving around and tumbling. So net result is the magnetic field on this nuclei, they are also changing with time. So such magnetic field which is changing with time very fast, how does that affect the nuclear spin? The actual details are quite complicated. You have to do a lot of mathematics to find out. But fortunately, they have very easy to understand effect on the nuclear spin. Imagine that all your nucleus spin, just imagine their collective magnetization. When you do nothing, they are along B naught, along the Z direction. We know that we call it magnetization. Magnetization in the equilibrium is always along the Z direction. And then suppose you applied a pulse, a 90-degree pulse along the X direction. Then that too we know what happens. It rotates by 90 degree, and it rotates in a kind of anti-clockwise about X-axis, so it will come here. So magnetization will be in the transverse plane. You know that because we mentioned that several times when we were talking about spin echo, that you rotate the magnetization and then you create what you call a coherence. These coherence or the magnetization that is in the transverse plane, if you just let it be, then I mentioned that it rotates very fast and it goes in a spiral and it goes to zero. That is what happens. And if you are in the frame of the magnetization, frame of omega naught, the rotating frame, then I mentioned that it does not rotate anymore. But then what happens to its decay? It still decays. It still decays. It's just going down in this direction. Instead of what you had the parallel, and now it's simply the magnitude is becoming first it was this much, then it's smaller, then it's smaller, eventually it goes here. So this is how it decays. So if I can plot the magnetization which is along the minus y direction as a function of time, I will see that it will start from some large value and then it goes down exponentially. This exponential decay has the same characteristic as our T2 decay. So it's basically essentially transverse relaxation that we discussed earlier. So this we know that the transverse decay takes place. Now, what is the connection of this decay and this electron spin? All right. So if you have paramagnetic spins there, and if the nuclei are being affected by the magnetic field of that paramagnetic ion, the electron spin, then they will decay much faster. This is with paramagnetic ion, and this one without. So without paramagnetic ion means, I mean, can we now draw the T2 curves? I mean, I'm calling these curves as T2 curve. Can we do that for like the protons in the oxygenated blood and deoxygenated blood? Can we do that? Of course, we can do that, and it will look very, very similar. Let's do it here. Or, I mean, we already have it drawn, so we can just mention that with paramagnetic ion. With paramagnetic ion means this would be our deoxyhemoglobin. And without paramagnetic ion, this would be oxyhemoglobin. So which means the oxyhemoglobin, which come in during the brain activity, they have slower decay rate. And typically, the deoxyhemoglobin, which is there all the time, unless effectively replaced by the oxyhemoglobin, their magnetization decay fast. This is called bold response. What is bold? A bold stands for blood oxygen level dependence, dependent actually. So, I mean, the bold response principle is the backbone of functional MRI. I mean, you see, there is MRI. A standard MRI does not care whether which part of your brain is functional or not. Typically, when they try to detect, say, for example, a brain tumor or any irregularity in the brain, they just put the person in and record image of a slice of the brain, and during that time which part of the brain is active and the patient, whether he is particularly having some activity in some part of the brain, that is nobody cares. So you can say the intensity distribution in that image is actually indicative of nothing. At least there is no controlled method. We are not controlling the patient, we are not forcing the patient to have a particular activity. So as such, that image, we do not analyze that for having some activity or not. If we want some activity to be monitored, then we have to do it this way, that we have to record two images. One is a control, the other is with activity, and the difference between the two will tell us that which part is actually active. Okay. So, but before that, you see, we already have this graph, and we identify that the new blood which is coming in, which carries the oxyhemoglobin, it decays slowly, and otherwise the blood which was already there, the deoxyhemoglobin, it has, and that is paramagnetic, so it decays faster. So this is the key part that we need to remember. Now, any question at this stage? If you have any doubt, any part you didn't understand, you can tell me.
So it's not with the theory, but when we see the MRI, then which part is dark and which part is whitish?
Huh. Oh, okay. You mean that if you actually do, if you look at the raw signal, then these, any part where there is no proton, that will show up as the dark area. Any part where you have lot of proton, that will show up as bright area. This is, I'm talking about the raw signal. But what you see is almost always not the raw signal. Almost always the contrast is calculated by subtracting some base value. The net result is oftentimes the skull shows up not as the black line, it shows up as a bright line. So the difference is highlighted. Usually it is basically, suppose there is a proton distribution, we call it a rho, then what you look at oftentimes is more like 1 minus rho. So you will notice that the portion where you do not expect any signal to come in, those portions show up as brighter. But does that matter? I mean, does it matter that actually we are looking at the wrong thing? Actually, no. I mean, what is important is some sort of image. See, we do not look at explicitly where the gray matter is and how does the small things change. What we look at is whether there is a big blob like a tumor, or there is some kind of lesion, some some damages. So those, whether they color come up with a bright color or dark color, usually doesn't matter. As long as it is different from the control image, we say, okay, there is something. I mean, that is normally what we do. Okay.
Okay. Yes, sir.
Okay.
And so the spectrum, when it is recorded, it is how is the peak? Is it the box shaped or the triangular shape, that pyramidal shape?
Can you repeat, please? I'm sorry.
So when we record the spectrum, it is the box shaped. The how does the spectrum look like?
Okay, the spectrum for the projection reconstruction.
Yes, for the
For the
brain.
projection reconstruction, when we do that, I mean, it would be quite complex. You will have many, many peaks, and it looks a complicated stuff like this. Hmm. There would be many such, and when combined, that gives you, a full detail with the skull visible, and then these matters inside they're also visible, and some dark areas between the left half and the right half. I mean, that is how it shows up. But individual slices, spectrum, they look quite complicated, not like our simple 2:1 kind of stuff. It's much more complex because there are so many things inside.
Okay, sir. And so when the person is objected to this magnetic field, so does it have any side effects on the body? Though we get the image that I understand, but the person is
If
exposed.
the person is inside the magnetic field and
Mhm. So and so is there any side effect of this?
oh, okay. Yes, side effects are many. Many people complain that they can hear noises, some weird type. Some of them say it's so unbearable that they can't undergo MRI. So that kind of things are there, which are not very well understood. That what's happening. Some people say this magnetic field play around with the neuronal signal, which are actually electric activity, so it affects the motion of the electron inside the neuron, so that can have some effect. But these effects are temporary. There are no lasting damages coming from MRI. So side effects are those, but it's not very well studied because some people say they don't have any problem at all. Hmm.
Mhm. Okay, sir. Thank you, sir.
Okay, so I move on to the what I was saying earlier. We have two graphs now, T2 graph. So I'm plotting magnetization, suitable direction, the magnetization decaying at two different rate depending on where we are looking at. If we have deoxygenated blood, then it decays faster. If we have oxygenated blood, it decays slower. But how that does that help record the image? It's quite simple actually. So what we do is first, we apply I'm giving you a simplified form of what actually takes place. So you apply this sequence first. What happens? A 90-degree pulse, after that the signal goes down. Then you have the 180-degree pulse. This 180-degree pulse, remember the spin echo sequence, it helps refocusing everything. So which means the magnetization is coming back here and then it will decay again. This is what is happening. So we record the spectrum here. Okay. So this remember this height of the echo that we are getting, that will depend on where we are and what kind of blood we have. So maybe I will. So suppose we consider our boxes, simple boxes, three boxes, and or rather even simpler. We have two boxes. And if we record a spectrum Typically, we would expect this 1:1 image like this. And how did we record that? I mentioned that you have to apply a gradient along this direction, and then uh, they have different Larmor frequency, smaller and bigger. So you record that, you keep changing the photon frequency, and whenever there is a match, it will show up as a peak, and you record this. What I missed here is also what I did not mention, that the intensity of these peaks will also depend on initially how much coherence you created, in the sense that it's slightly more complicated than that. So what we do is something like first we apply a 90-degree pulse. You see, we did not apply the gradient yet. So this 90-degree acts on this box and this box also. Then we apply, we wait for some time. So magnetization in both the boxes, they kind of decayed down. Then we apply 180-degree pulse, and then the magnetization refocuses. So after the 90, 180-degree sequence, we have something in both the boxes. Both the boxes have some magnetization. This is what we detect. We record the spectrum. So you can say this intensity here will be proportional to the T2 decay. Say for example, suppose this gap is tau, and this is also tau, so that we started recording the spectrum actually 2 tau time after the 90-degree pulse. Then what we need to do is, here we need to look at the time after 2 tau and find out what signal intensity will we have. Okay, we have to use this curve as a calibration curve. Now suppose we have boxes. This box has the deoxygenated hemoglobin, and this guy has oxygenated hemoglobin. So what will happen? This is the oxygenated hemoglobin, and this is deoxygenated hemoglobin. So if we do this experiment, then the deoxygenated hemoglobin for that T2 curve is sharper, so which means, it falls faster. So after some time, tau 2 tau, we will have less signal, and oxygenated blood will have more signal. And now we are recording the image. At this stage here, at this point, we apply our gradient and record. So we are doing this with the echo signal, and echo signal depends on whether we have oxygenated or deoxygenated blood. So this will have less signal. This will have more signal. So instead of our control spectrum, where both are equally intense, okay, so assuming initially both were like deoxygenated, let us do that. Both were deoxygenated. Then what will happen? After this, both will have this much intensity. So I will have some intensity here, small, some intensity here, small. That's it. And then if this one gets replaced by oxygenated blood, and we do the same experiment, then the first one, the intensity will remain same, but the second one will have much higher intensity. So we will have higher intensity. That's fine. So if a simple question is asked that which of the box is more active, some activity is taking place in which of the box, you would be straightforward. You can answer that. You would say it's the second one, because during the activity, the deoxygenated blood was replaced by oxygenated one, and oxygenated hemoglobin is diamagnetic, and because it is diamagnetic, it interferes less with the nuclear relaxation. So net result is that the magnetization decays slowly. So it gives us more signal. It's very good. So what is the next step? Next step would be take the difference between the two spectrum. So if you take the difference of the two spectrum, what do you get? You get 0 here, nothing. And here you have some something. So you would say this is fMRI, the functional MRI I recorded. I found that this is the place where some activity is taking place. This is the simplest 1D image that I can record. Of course, in actually in either Kolkata, such simple 1D spectrum, and particularly 1D images, and where we have a different kind of sample, something here and something else there with different T2 values, we have actually recorded that. So it's not just what I'm showing you is like um, a test uh, situation only for the sake of taking the class. No, I mean, actually, some of our publications do have images like where we have a tube, or we fill part of the tube with one substance and other part of the tube with another substance, and they do have a different T2. Some maybe this one has smaller T2 and this one has larger T2. And if you record the image, you do see initially when the effect of the T2 is small, for small delay value, you would expect both to be equally intense. So your image looks like this. But if you do that after some time, then what you get is uh, the first one, of course, decayed, and the second one, it did not decay. Its T2 is longer. So it did not decay much. This one decayed a lot. So this difference is quite visible. So you can say this is like a T2 contrasted 1D image. If I can take a difference of the two spectrum, of course, after I scale it to this level, if I do that, then only the remaining portion will show up as the active region. In our case, there was no activity going on. It was like permanently we replaced the deoxygenated blood by oxygenated blood, and this is why we could see that. But this is just a demo. So we actually do that. We oftentimes we record such spectrum. So what I show you is basically the simplest possible way of finding out some region which is active. Okay, so this is the bold response technique. So, I mean, to summarize, what does the bold response technique depend on? First, you have to do a spin echo sequence. Why you need that? Because you need everything to be T2 weighted. The word is T2. You'd like to weight your image by T2. So that means higher T2, one weightage, lower T2, some other weightage. So if you have the T2 weighted image, then if you have, you are recording image, then if you have multiple region, some of the region have a larger T2, they will give you better signal like this guy. And some of the region has smaller T2, they will give you a smaller signal uh, like that one. And their difference will tell you that where you have the activity going on. That's basically the principle of functional MRI. There's nothing more to tell you except the operational principle. Operationally, how do you make sure that some part of the brain is active? But that's trivial. Anyway, I mean, you get to ask question once more at this stage if you have questions. Not much. All right, no problem. So I'm kind of done with what I wanted to tell you, that you need T2 weighted images for getting the functional MRI. So that part is kind of done. Now the functional aspect, meaning how do you record the control and how do you record this actual one. So what you do is there are two things. Control means, does it require a person not doing anything, a truly basically flat brain response? That is extremely difficult. It's extremely difficult even when we sleep. Something is going on and it's nearly impossible to make sure that a person is not thinking anything. I mean, that's extremely difficult. But if you look at this curve, you already know the answer. That if I can record a spectrum without doing the spin echo, immediately after the 90-degree here itself, instead of waiting for spin echo, no spin echo at all. I mean, we do it immediately after the 90-degree. Then what will happen? Then if nothing has decayed, the coherences, the magnetization, they did not have time to decay. So which means oxygenated, deoxygenated, both give you a similar response. So then maybe we record a spectrum, an image with very small delay. Yes, if you can do that, then you get more or less a nice balanced picture and no issues there. Plenty of signal from each places. Very good. And then what you do, then you ask the person that to, I mean, like to engage in some activity. It could be like you play a song, you ask the person to focus entirely on the song, or you show some images, you ask the person to look at the images. Remember, watching the image is difficult in the sense that if some person is inside the magnetic field, then you can't go in and show some pictures. So what you do need to do is you fit some non-magnetic contraception. The person is inside the magnetic field. Maybe you put some mirror there, non-magnetic material, so no metal there, and the person through the mirror would be able to see some picture that you have put at the back of the room far away, and there you can change things and and make sure that a person has the attention on the picture. And then while he is focusing on that or processing that information, reading something, you record the MRI once more. So you record two MRI, one with very short delay, the other with a longer delay. A longer delay will ensure that you have your weighted images, and then you take the difference of the images. The difference will tell you, just like in this case you have, it will tell you where the activity is going on. So that is how you identify the active region using functional MRI. But is it a good method? Good method in the sense that does it actually detect the brain functions? It does not work always very well, simply because not everybody's brain is exactly identical. And then even when you are playing a song, uh, what kind of activity brain is involved in, you do not know. I mean, like it's not, thought process cannot be controlled exactly that way. So there are some issues there, but physical principle is robust. What I described you, irrespective of what is going on inside the brain, I mean, like thinking process, I'm saying, but the response of oxygenated blood or deoxygenated blood, these are well regulated, no doubt about that, and it more or less works. The only downside is MRI takes a bit of time. Some people say they are uncomfortable. Some people feel claustrophobic going inside a narrow chamber, which is not a nice feeling. So, I mean, those are the disadvantages. But otherwise, if we disregard all those disadvantages as a method, it's quite robust. It works very well. It's well studied and it's known for a while now. So basically that, this is what I wanted to share. So I'm kind of done. So now what I'll do is, because the physical principles have been covered and etc. So you ask questions. If you have questions, you can ask questions. Polite. So in any case, because the major part of the lecture is over, Maybe I can stop the recording and I'll be here. I'm not going away. I'm just stopping the recording.